Hi everyone, we're going to get into the ideal gas law, part of chapter 1. So let's move into it. What we're doing is we're starting with a very broad theory of gases. Remember, a theory is a way to explain a phenomena. When we talk about the phenomena with gases, we're talking about their behaviors relative to liquids and solids. And in a very broad sense, this kinetic theory of gases is that gases move a lot more than liquids and a lot more than solids. It's basically what this theory says, is that gases are very, very small molecules that have a lot of energy and that move around quite a bit, much more so than liquids and much more so than solids. Their movement can be random and it can have structure imposed on it, but there's a lot of energy there for a lot of small particles, the kinetic theory of gases. Now, there's also a theory about ideal gases. We want to talk about that next. Nitrogen and oxygen, which are more than 90% of our Earth's atmosphere, are known as ideal gases. What are ideal gases? Ideal gases are like the pool balls on a pool table. They are gases that are so independent and so non-bonding that they are like the pool balls that knock into each other and just go their own way. They don't share energy at all. They don't share bonds at all. They don't move together. Like these pool balls will never seem to glue together and move together. That's not the way pool balls are. They just bang into each other and they move off of and away from each other. They don't interact at all. That is like an ideal gas like nitrogen and oxygen in our atmosphere, specifically like N2 nitrous dioxide and O2, which is oxygen in our atmosphere. They don't bond with other molecules easily. They do their own thing. They're not known for their interactions. Now you might say, why is that? It's because of the bonding structure between nitrous dioxide and between oxygen. Nitro dioxide has 3 bonds to it. Incredibly hard to break those bonds, though it can be done, especially in polluted atmospheres. But it's very hard to break nitrous dioxide bonds. And so that is replicated with oxygen, which has a double bond, very happy electron shells, very stable molecules that are not looking to interact with other molecules. As a result of this, 2 independent ideal gases that don't interact with each other, when you have them side by side in an atmosphere, you tend to have additive pressures of nitrogen dioxide and of oxygen, and additive quantities, number of molecules of each gas, of each of these ideal gases, and additive volumes of each of these ideal gases in one atmosphere that we have in around our Earth. These 2 ideal gases make up more than 90% of our atmosphere and really completely diminish the impacts of the other 7 or 8%, which include argon, which is relatively inert anyway. Argon is practically an ideal gas, and water vapor, which is not an ideal gas, but there's so little of it, between 1 and 4%, and CO2. And CO2 is definitely not an ideal unreactive gas. CO2 is quite reactive, but when you see the percent of CO2, it's less than 1%. So we talk about the great effect of the 92% of the ideal gases, and that overall our atmosphere functions as one ideal gas. And in talking about that, we can talk about the predictability and the relationship of the behaviors within that ideal gas. And those behaviors include high and low pressure, high and low volumes of gases, high and low density of air, and a stable temperature. So we talk about air masses of this ideal gas, this ideal air, and we talk about high and low pressures of those air masses, volumes of those air masses, like a large cold air mass coming in from Canada, you hear about that, and density of those air masses and temperatures of those air masses. You hear about cold air masses coming from Canada, warm air masses coming from the Gulf of Mexico. So these are behaviors that are predictable and relative to each other. They have relationships between pressure and temperature, between volume and density. So let's talk about it a little bit more. The relationship is known as the ideal gas law, and a law, remember, is a mathematical concept that explains mathematically a phenomena. So you have a theory which explains the how and why of the phenomena, and a law which is the mathematical calculation or concept of the phenomena. In this case, the ideal gas law is probably one that you've heard about, PV equals nRT. We're really going to dig into it because meteorology is all about PV equals nRT. P is pressure of that air mass. V is volume of the air mass. N is the number of molecules in the air mass, which is so great that we use a unit of measure called a mole instead of trying to count the molecules of the air mass. R is a gas constant, which you can effectively just throw out because it's constant whenever we use it. And T is the temperature of that air mass. It could be cold, it could be warm, it could be hot, and we will take the temperature in Fahrenheit and in Celsius in most cases. Now let's start with what you know about how these behaviors are related to each other. And one thing you do know is that overheated tires pop during the summertime. They pop because they overheated with those hot temperatures and the pressure went up in the tire and blew it out. So you know this, and now we can look at it mathematically with PV equals nRT. And it makes sense that when the temperature goes up on one side of the equation, the pressure is going to go up on the other side of the equation. All right? So that's what an equation is all about. When one side goes up, something on the other side has to go up as well. In this case, the number of molecules of air in the tire before it exploded was constant. So there's two constants here, and the temperature went up, and the volume of air in the tire before it exploded was constant as well. Nobody was pumping air into the tire. The volume was constant. That means the pressure was the only thing that was left to go up. But you knew that. We went over that, and that relationship, temperature up, pressure up, is known as Charles's law. Okay. Let's go with another relationship between volume and number of molecules. This is an easy one, just based on breathing in and out. And start with what you know. You know that a deep breath feels really good and gets a lot more oxygen into your body. So you have taken in a volume of air, and you've also taken in more molecules of air, which is completely intuitive, and it makes sense with our equation. As volume went up, the number of molecules went up as well. The temperature changed a bit between the outside air and the inside of your body, but it's not nearly as constructive or as important as the change in volume related to the change in the number of molecules of air. So that's an easy one. That's a behavior that you know. Here's another one that you know about, the relationship between volume and pressure. Think about a soda can, pop-top soda can. When you pop the top, you're releasing the pressure, right? That was a pressurized can. And if you've shaken it up, it's going to fizz all over the place. what's really happening there? You're releasing the pressure, and the pressure is decreasing, and the CO2 is expanding out and taking the liquid with it. So in this case, the pressure of the CO2 is decreasing when it's got more area to cover, and the volume of the CO2 is expanding out. The pressure is decreasing, click, and the volume of the CO2 is expanding out of its pressurized zone. That's what you know intuitively. Now let's look at it from a mathematical point of view, because one is going up and one is going down. Hard to see. Not all that hard to see. PV equals nRT. We have P and V on the same side of the equation. That's not going to work for us because we can't compare them there. We need one on one side and one on the other side of the equation to compare them. Okay, so we can multiply by the inverse and get rid of the V. You can multiply both sides by V, and you end up with P equals nRT over V. Okay, that works. And what you see is that when volume increases in the denominator, that means that the quotient, the P, is going to be reduced. You say, how does that work? Well, let's look at it. If I said that my volume increased, I could take my volume in the denominator from 2 to 4. Well, if I did that, my quotient would be reduced because 1/4 is much less than 1/2. So as the denominator increased, the overall value of the quotient decreased. As volume increased of CO2, pressure was decreasing. All right, there's an excellent video on this. There's a link here on your PDF, so take a look at it. We already went over that, and I'll see you on the other side.